Looks good.
Excellent. Yeah, so thank you, Mark. As Mark said, my name is Brad Fraser from DST Group, and I'll be talking about our 4D nav paper. This work was conducted at DSTG Edinburgh in South Australia with Philip Moss and Kent Rosser. So, given the highly regimented and controlled nature of military operations, the ability for unmanned aerial systems to meet mission requirements in terms of their spatial and temporal locations is very important. In a single vehicle case, for example, a surveillance aircraft might be required to be on station at a particular time. This objective, of course, can be achieved using just-in-time logistics, where the asset is deployed immediately before it's needed. But this assumes that the asset itself and any launch requirements are available at that time. In some instances, such as restricted launch windows due to weather, it may be favourable to launch an asset earlier than it's needed, but still have it meet mission timelines. This then requires trajectory planning to ensure temporal timelines are met, which can be a burdensome task for human operators. In a multi-vehicle case like the HADAR Humanitarian Assistance Disaster Relief scenario we have here, there may be no communications between UAS and they may be launched from different places and at different times, but we still want them to meet at the rendezvous. A more selfish motivation for this work, I guess, came about when we were conducting other multi-UAS experiments. And we simply wanted the aircraft to automatically land in a sequence at a specific time. And we'll find surprised to find that current open source flight control libraries were missing this feature. So we went about trying to design, a practical, straightforward, and hopefully light implementation to incorporate into these libraries. So the problem on the surface sounds quite trivial. From point A, we want to arrive at point B in time t, noting that a fixed-wing aircraft, of course, can't hover. So we inject a loiter waypoint W with a radius R with a number of turns n, and you want to move at speed v. So looking at this problem, it's very underspecified. So you've got 5 free variables there to play with. So we can pose this scenario as an optimization problem where the objective function just consists of all the distances the aircraft has to travel, divided by its speed, of course, minus the time, and therefore a function value of 0 implies arriving at the perfect time. Posing the problem in this manner is useful since we can add constraints and bounds on the variables involved. So we can constrain where W is and its radius, as well as making sure, for example, the airspeed of the aircraft is within limits so that it stays in the air. Unfortunately, by posing the problem in this way, specifically constraining n to the set of positive integers causes the problem to become an integer programming problem, which are notoriously difficult to solve. So as a hack to get around this, we simply solve this optimization problem in a loop, incrementing n until a solution is found. In order to brake smoothly from the loiter and prevent the aircraft from making sharp turns or U-turns, which are difficult to model, we make sure the final position where the aircraft brakes from the loiter is tangent to the final location. So this introduces a partial distance of the loiter circumference, but can be readily calculated with the law of cosines. The algorithm itself is again quite simple. We simply, based on the current wind conditions, work out if the autopilot, gathered from the autopilot, we work out if the aircraft can slow down enough. Again, noting that the aircraft must maintain the minimum airspeed to stay in the air. If it can, problem solve, we just use that. But the more interesting case is when we have to inject this loiter waypoint. In our implementation, we use the SciPy library to do the optimization. And once broken from the loiter, the aircraft continually adjusts its speed as required to make up for any discrepancies in the model distance that we've accumulated so far. The aircraft can be commanded into a loiter using mavlink commands. This is assuming an Ardu type autopilot using nav loiter time or nav loiter turns. But unfortunately, it was found during testing that neither of these commands engaged the loiter timer immediately. And so we had to manually keep time within the aircraft companion computer and then again manually break the loiter when we needed to. We were trying to make use of, in building the trajectories, we're trying to make use of the autopilot commands as much as possible. So in our experimentation, we used the DroneKit Python library, which is an interfacing library to the autopilot, again, using mavlink commands. It's provided and was maintained by 3D Robotics. So the DroneKit library allows us to access wind speed conditions. However, we needed to extend the library to access the wind messages that the autopilot produces, noting that DroneKit was originally developed for the control of rotary wing drone type aircraft, which typically don't measure wind speed. We can also use the interfacing library to access autopilot constants, such as the minimum and maximum airspeeds of the aircraft. And we use it to upload the edited missions, which contain the injected waypoint. We conducted simulations using the Ardu plane software in the loop environment, which provides the best estimates as to what will happen in the real world. Simulation experiments used windy and windless conditions. In the windy conditions, the direction and speed were constantly changing to make it nice and hard for the algorithm. And the image on the right shows a single run of one of these simulation missions. The red trace shows the distance to be, obviously with the oscillation being the loiter. The other two traces show the ground and airspeeds of the aircraft. DroneKit actually supports the setting of the ground speed, which is automatically translated via the autopilot into a desired airspeed. So it makes things a little bit simpler from that point of view. Our field experiments, or perhaps evaluation for those that have just watched Peter's keynote, we used a 1.5 metre wingspan FX61 aircraft, so a fixed wing aircraft with 900 kV props and a motor and a 9-inch prop. 6 amp hour battery, nice and big, provided ample flight time. And again, a 3D robotics autopilot running Ardu plane controlled the actual aircraft. And we had an interfacing companion computer, a Raspberry Pi 4 as a companion computer, which communicated via a serial link. We also used an RF Design 900 bus serial modem, which provided a control down to the ground control station. And of course, we had an independent control link back to a safety pilot in case things went pear-shaped. So the graph on the right shows the results for windy and windless conditions in simulation, as well as the field experiments. And the box plots show the arrival time discrepancy and therefore should be as close to 0 as possible. And in general, we see reasonably good results in simulation, but there's a slight discrepancy in the real world. So as we all know, sim to real is a difficult problem. And there also appears to be a slight bias to being late, which I suspect is the result of an algorithm timer issue in the implementation. The bottom image in this slide shows the outcome of a single run of a real-world experiment generated using mission telemetry. Waypoints 5 and 6 represent A and B, while waypoint 9 represents W. To facilitate testing in this scenario, W was fixed as the midpoint between A and B, just to make things a bit more deterministic, so we knew what was actually going on and where the aircraft should go. That wasn't taken into account or wasn't calculated by the optimizer. As we can see, there is some variation in waypoint tracking, as well as in the waypoint loiter, as the autopilot attempts to hold the requested parameters. And this, of course, contributes to unmodeled distance and therefore error in the time. We can see here, moving from left to right, the tangent waypoint braking worked reasonably well in this instance. So in conclusion, the mean rendezvous error was found to be 1.2 seconds late from 130 simulated runs with windy and windless conditions, and roughly 3 seconds late from 10 field runs in a single flight. The experiments themselves require a tighter error control for environmental wind speed variability and trajectory tracking. So again, this comes back to Peter's point, I guess, about repeatability. However, depending on the application, and at least for our application of landing the planes in sequence, results were within our tolerance. The model could be improved by taking into account acceleration and deceleration rates of the aircraft and things like that. And finally, the parameters for optimization success were quite loose to avoid large compute requirements, and we didn't need a solution down to a lot of decimal places. So even though the optimization was quite light, we need further investigation to see if it could actually be deployed on the autopilot hardware rather than the companion computer. I'd just like to thank Warrant Officer Wayne Newbury from the RAF Active Reserve and number 453 Squadron RAF for helping us with the flight experiments. Thanks very much.
Thank you very much, Brad. So just a reminder to put your questions onto Slack. So we've got a bit of time for just a few quick ones. But I'll ask a question. You talked about the motivation for this project coming from a lack of functionality in the tools you were using. I don't know much about the platform you're using. Is that open source? And is there any opportunity for you to provide those tools for others to use?
Yeah, absolutely. The Ardu project provides, basically autopilot software for ground, for plane, for underwater, for subs and things like that. And it's all open source. The Maverick command project is all open source as well. And so, yeah, definitely at DST, a lot of my colleagues contribute quite heavily to those open source projects. Again, so this is kind of why we were looking for a simple, straightforward solution that we could actually push back into the open source community.
Fantastic. Just checking if there's any questions on Slack. I don't see any there, and for the sake of time, we might move on. But if you did want to ask any questions to Brad, please put your questions there, and I'm sure he'll be more than happy to answer.